Hello and welcome to this video. Today we will solve a Leetcode problem called valid arrangement of pairs. Let's look at the problem statement. So in this problem, we have been given a zero-indexed two-dimensional array of integers called pairs, where each element in the array is another one-dimensional array which contains two elements each. The arrangement of pairs is considered valid if for every index I, where I ranges from 1 to the number of pairs minus 1, we have end of r minus 1 equals to start of I, and we need to return any valid arrangement of pairs. We must also note that the inputs provided are such that there always exists a valid arrangement of pairs. Let's try and understand this with some examples. So in this example, the inputs have been provided and the output expected is a two-dimensional array, and each element in the array is a single-dimensional array of two elements each. You'll notice that the first element in the output is 11, 9 and the second element in the output is 9, 4. So you can see a sequence here, 11, 9, 9, 4, and similarly 9, 4, 4, 5, and finally 4, 5, 5, 1. So this is what is considered a valid arrangement of pairs. To solve this, we need to think of structuring the input as a directed graph. Once we have a graph, we then need to walk through each node exactly once. Such a path is called Eulerian path. From the definition from Wikipedia, in graph theory, an Eulerian trail or Eulerian path is a trail in a finite graph that visits every edge exactly once, and it allows for revisiting vertices. So here's the Eulerian path for the example we just spoke. Once we form this path, we can simply recreate the pairs by combining the numbers as follows. Firstly, we'll create a pair with 11 and 9. Next, we'll create a pair with 9 and 4. And then 4 and 5 and 5 and 1. And this way we will get the valid arrangement of pairs. To understand how we get to this, we need to look at some graph basics. This will help us solve the problem. The key concepts in graph theory are graph, vertices, edge, degree, and the way to traverse, which we'll be using in this algorithm today, is depth-first traversal. So what is a graph? So essentially, a graph is a structure of related objects called nodes or vertices, such as in this example, A, B, C, D, and E are vertices or nodes. The lines connecting these nodes are called edges. In this example, the lines have arrowheads which point to specific nodes. Such a graph is called a directed graph. The degree of a node is the number of connections to it. In the case of directed graph, the number of outgoing connection is called out degree, and the number of incoming connection is called in degree. If a node does not have any incoming connection, we can think of it as a start or root node. So firstly, let's calculate the in degree for each node in this graph. So here's the graph without the arrows. So if you see, there's a link from E going to A, and that's the only incoming connection into A. Therefore, A has an in degree of 1. B has in degree of 1 as well because it has just one incoming edge. Similarly, C has 1. Now D has incoming connections from A and C. Therefore, it has an in degree of 2. Finally, E has an in degree of 1. Now let's look at how we can traverse this graph using depth-first traversal. Depth-first traversal traverses a graph in a depth-first manner. The algorithm starts at the root node and explores as far as possible along each branch before backtracking. The most common way to find the start node to iterate is to pick the one with no in degrees. If no such a node exists, we can select an arbitrary node as the root node. So how will depth-first traversal work for this graph? We start with A, then we go to B, next we go to C, then we go to D, then we go to E, and then finally we go back to A because there was a connection to A. And there is also another connection from A to D, but since D has already been visited, we don't add that into our visited nodes list. So that is the basic concepts. Now let's look at the algorithm which we will be implementing today. So firstly, we need to build a graph. Next, we need to identify the root node for this graph. Once we have identified the root node, then we can depth first traverse from this node. Once we have iterated through all the nodes and we have the Eulerian path, we can simply recreate the pairs and return. So we will look at building a graph from a two-dimensional array. For this, we will use a map to represent the graph. And a map contains key value pairs. So in our case, we'll use the start node as the key, and we'll store the end node in the list which will be stored in the values in the map. So for example, if you look at this two-dimensional array, the first pair is 1 and 2. So 1 is the start node, 2 is the end node. So 1 becomes the key and 2 becomes the value. So similarly, in the second pair, 2 becomes the key, 3 is the value. So if we continue this way, we'll also see that we have a pair 1, 4 at the end. So 1 is already present in the map. So because we have another element visited from 1, we'll store it in the list of nodes under the key 1. To find the start node, we can first check the number of incoming and outgoing connections to each node. Let's use a measure called degree. For an incoming connection, we increment the node's degree by 1. For an outgoing connection, we decrement it by 1. So in this case, the node 1 has 1 incoming connection and 2 outgoing connections. So the degree is 1 minus 2, and that is minus 1. Node 2 has 1 incoming and 1 outgoing connection, so its degree is 0. Similarly, we can calculate the degree of all the remaining nodes. So if we have a node with degree of minus 1, we can use that as the root, else we can pick any arbitrary node. Once we have identified the root element, we then traverse using depth first traversal. So traversing this specific graph, we get the sequence 1, 2, 3, 4, 5, and 1. Finally, we recreate the pairs using this sequence. Firstly, we pair 1 and 2, then we pair 2 and 3, 3 and 4, 4 and 5, and 5 and 1. So if we put this in a 2, so this is the valid arrangement of the pairs that we need to return. So let's jump into the code and implement this algorithm. To allow me to test my code, I've created a simple Maven project and added libraries which I'll be using to write unit tests. So this is the section which contains the libraries. As you can see, I'll be using JUnit for writing the unit test and the assertions library assert_j core to add assertions in my test. I'll start by adding a new class to my project. Now I'll add a method which takes the 2D array and returns the 2D array back with the pairs in valid order. So here's the method which I have added. It's currently not returning any valid data. I'm going to add a test which can use to drive the implementation. So here's my test which verifies that given an input, it produces the correct output. So as you can see, the input contains the pairs 5, 1, 4, 5, 11, 9, and 9, 4. And I expect that when I pass this as the input, I am given back this output, which is the pairs arranged in the correct order. So for that, I'm firstly creating an object of the class I'm testing, which is valid arrangement of pairs. Let's just call it V. and I'm passing in the input to this method valid arrangement, I'm getting an output back. And finally, I'm checking that the output matches my expected output. Now, obviously, this test is going to fail because I have not implemented the functionality. But let's see the test failure, and then we can go back and implement the test. So, as you can see, the test is expecting the output to be this, but we are getting the empty 2D array. So here I'm back in my class, and we will implement the algorithm which we just discussed. So firstly, I'm going to define a couple of fields for this class. So the first field that I'm going to define is the graph, which I'm going to represent using a map. So the graph essentially is a map here with the key as the node, and the values for that node will be the list of its neighbors that it is pointing to. The second field that I'm going to define is the degrees for the nodes. Now let's break down the algorithm into a few methods. So firstly, I'm going to write a method to build a graph and the degrees. And the parameter will be the input parameter to this method. What this method will be doing is essentially building out the values into the graph and the degrees. So to build a graph, we need to iterate through all the pairs. Let's get the start and the end element in this pair. Next thing we need to do is store the start element in the key as the key of the map. But we need to do it only if it doesn't exist already. And the value for this node will be an empty list. Because we haven't identified the neighbors yet. The next step is to actually add the neighbor into this list in the graph. So let's first get the list for this element and then add the neighbor it is pointing to. So when we are doing the graph.getStart, it is returning the list for the key start, and it's then adding the neighbor end to that list. Next thing is we'll start adding values into the degrees map. We'll start off with the value 0. And now what we need to do is, if you remember from the slides earlier, for every incoming connection, we increase the degree. For every outgoing connection, we decrease the degree. So in this case, the start element is pointing to the end element. That means there is a outgoing connection from the start element and there's an incoming connection to the end element. What this means is we need to decrease the degree of the start element and increase the degree of the end element by 1 each. And because the start element might already be present in the map, we're going to get it first out, which will get us the value 0, in this case if it's the first time, otherwise a different value, and then you subtract 1 from it. For the end element. We start with 0. And we increase the degree by 1. And that is all we need for building the graph, because this code will iterate through all the pairs and build the graph and the degrees using the input 2D array. Once we have the graph, the next thing we need to do is find the root node. If you remember from the slides earlier, the best candidate for the root node is the one with the -1 degree. But if there isn't such a node, we can simply pick a value from the list of nodes. So what this method will do is it will return us a root or start for the depth first traversal. And we also want to make sure that if there is no node with negative degree, then we can just provide it with some default. So I'm going to pass in one default value, which is the first one. So in this case, I'm simply passing the first element from the first pair as the default value. So let's implement this method. So the value I'm going to return, I'm going to call it root. And initially, I'm going to assign the default value to it. And that will also be the return value for this method. Now I'm going to loop through all the degrees and pick the one which has got a degree of -1. That we can use as the root node. So I'm going to check if the value in the degrees map is -1, and if it is, then I'm going to use the key as the root node. Actually, I'm going to call this entry rather than entry set. We'll go in refactor, rename, let's call it entry. Get the value, and if it's equal to -1, you can say root equal to entry dot get key, and we can break from this loop. I'm going to fix this compiler error because it's complaining about the casting. So if you hold the mouse, you can see that it's trying to compare an object with an int. So that is all we need to get the root node for this graph. Now if you remember the slides, I was showing the Eulerian path, and we're going to use depth first traversal. So I'm going to add a method which takes in the root element of the graph and then simply returns the list of nodes traversed using depth first traversal. So here I am calling a method and passing it the root node value. So let's define this method. So for doing the depth first traversal, we can use a recursive method. So if you remember the slides, the algorithm for depth first traversal works by visiting every node there is to visit. So we would need to use recursion and pass it the list of neighbors for every vertex. For that, I would need to create a list of traversed elements and pass it into the recursive method. So let's do that. And the recursive method can be called depth first traversal. And we'll simply pass in the root and the traverse list. And we just need to return the traverse list from this method. So what the depth first traversal method will recursively call itself on all the nodes, and as it goes through the nodes, it will add them to this traverse list. So let's define this method here. So firstly, I'm going to get the list of neighbors for this element start, and that is available in the graph. Let's call it neighbors. Now we need to loop through all the neighbors. So we loop through the list till there's nothing left in it. Let's get the first neighbor in this list. Let's just call it next, because we are in a loop, and every time we loop through the list, we'll just get the next, next, and next. Once we have visited this neighbor, we can mark it as traversed or visited. We do that by simply removing this element from the list of neighbors. And now we simply call on the current neighbor. Once the traversal for a node has finished, we need to also add it into the traverse list. I'm going to add it at the index 0 so that every time a new node is visited, it is at the same position, and that way the newest node is at the beginning of the list. Now that we have finished our depth first traversing and we have returned the traverse list back into the valid arrangement method, we need to now build the two-dimensional array with the valid pairs arranged. So now let's loop over this traverse list and build out the array. Let's call it arranged pairs. So the original input was pairs. The return value is arranged pairs. And the first dimension is the number of pairs. And the second dimension is 2 because every element in the 2D array has 2 elements. Now let's loop through our traversed array. Before we go any further, there's few things to notice here. So we're starting with the index 0 and we are going till the size -1. That is because we need to go till the position 2 places before the end so that we can grab 2 elements. The other thing we need to note here is that traverse is a linked list and not an array list. So iterating over an array list is much more efficient using index values, whereas iterating using an iterator or a linked list is more efficient. That is because an array list is backed by an array and the values are stored in contiguous memory location. So let's first implement this and get the test passing, and then we can remove the inefficiencies which we just discussed. So here you can see the first pair is the value at the index I, the second pair is the value at the index I plus 1, and this is why we need to stop the loop at size -1, so actually before size -1, otherwise it's going to run into problems where it's trying to access the element outside the bound. Finally, we can return the arranged pairs. Let's go back into the test and see if it's passing. Great. So now coming back to the issue here, so you can see that I'm using the index for iterating over a linked list. The simplest thing I'm going to do is transform this linked list into an array list. And just provide the initial values from the same list. So what this will do is build us a new array list using the values from the linked list, and we're simply assigning it back to the same list. And if I run my test, it should still pass. That's great. So let's go over to this algorithm very quickly and then we can wrap up the video. Firstly, given the pairs or the two-dimensional array, I'm building the graph. Once I build the graph, I'm finding the root node of the graph. Once I found the root node, I'm getting the elements in depth first traverse manner. Once I've got the elements in the depth first traverse manner, then I'm building pairs out of this list. And thank you very much for watching. If you like this video, please consider liking and subscribing, and see you in the next video.